1,000 times a year, volunteer lifeboat crews like this one get sent out all around the waters of the UK and the Republic of Ireland to perform rescues. But each time they go out, they rely on one fact, that 12,000 miles that away, in what's called a mid-orbit, a 27 global positioning satellites. Okay. How much more difficult would your job be if you didn't have GPS?
With the GPS, you get a casualty call up, you've got their position straight away, put it into the satellite system, gives us range, bearing, distance to run, gets you to where you need to be straight away. Time is lives, absolutely vital to our saving work.
The American GPS satellites work alongside another Russian system called GLONASS. And to explain all, I'm meeting a GPS expert at a satellite tracking station in East Sussex. How does it all work? When I punch in an address here and press go, what's going on?
So the first thing the device is doing, it's measuring the distance from here, from the receiver, out to those satellites. Second thing it's doing is tracking these signals broadcast by the satellite, which is telling the box where the satellites are up in space.
So this is just like a radio receiver, if you like, picking up sort of radio signals, but these radio signals have data in them coming from satellites.
Exactly, that's right. So the satellite spits out a little blob of electromagnetic energy, and on that is like a time mark. It says, OK, I transmitted this signal at this time. And then as well as transmitting the time, it says, roughly, this is where I was when I transmitted the signal.
So you've got a very, very accurate clock in there?
Very, very accurate clock, yeah. And the receiver down here has also got a clock in it. So let's take the phone here, for example. Okay. So there's a clock in here, there's a clock in here. When the signal leaves the satellite, eventually sometime later on, about 77 milliseconds later on, in fact, this picks it up. Then the receiver takes a reading of its clock when the signal arrives. So the signal, the receiver knows when the signal got there, and it knew when it was transmitted.
So I now know where that satellite is.
You know two things. You know where the satellite is,
and what time,
and you know how far
away it is. Okay,
that's basically it.
Wow, you know what's just struck me is just quite, this fantastic infrastructure that supports all this in terms of satellites, in terms of ranging stations, in terms of big physics, in terms of big mathematics. And every time I turn one of these on in the car, I get a bit cross because it doesn't sort of work instantly. It's amazing. So why 27 satellites in orbit? Well, actually, it takes more than one to give an accurate location. In fact, it takes 4.
Imagine these are 3 satellites. So we've got a pink satellite, a blue satellite, and a green satellite. And we know the coordinates of where they are out in space. And the ropes represent the ranges.
We know the coordinates out in space because they've got very accurate clocks, which we can measure the time it takes to beam the signal back to Earth.
That's right. So the rope represents the range.
Okay.
So let's see what would happen if we had just one satellite.
Careful of your nice shoes.
Yeah.
Ah, OK, so with one satellite, we could be anywhere on this line, basically.
Exactly.
So, which is not much good.
So I know my receiver could be here, or it could be here. That's using one range from one satellite.
Let's bring in another satellite, then. Ah, because we've got 2 satellites where these points intersect.
That's right.
There, that's where we are.
So in 2 dimensions, that's going to be your position 6.
Yeah.
Now, of course, in reality, in space, we're trying to fix our 3 coordinates. So maybe so much along X, along Y, along Z, or eastings, northings, and height. So we need to make a measurement to a 3rd satellite. Let's do that.
So suddenly we have where these points all intersect. This is our location in 3 dimensions.
That's right. That's right.
OK, that seems pretty convincing. But where does the 4th satellite come in?
You use the 4th satellite to synchronise your little clock with the space clocks. The problem is to do with the quality of the clocks, because the clocks up on the spacecraft, they cost about $2 million each, and they're really, really good, really stable. The clock in your little GPS receiver only costs about 15 cents, and so it really doesn't keep time as well as the clocks up on the satellite.
So the 4th satellite really just there to sort of get rid of those margins of errors, get rid of those problems you've got.
And to make sure the satellites really are where they say they are, tracking stations like this one constantly fire lasers at them
as they pass overhead.
Dallas, fire that laser.
OK, I'm going to fire the laser. Ready? So really what we've got here, we've got a giant laser pointer, if you like. On the satellite, they've kind of got reflectors like cat's eyes. You ping the laser at the cat's eyes, it bounces the laser back. We know what the speed of light is, so we know where it is.
This device can tell you the range within, you know, 3 or 4 millimetres.
That's unbelievable.
Yeah, it's pretty cool engineering.
Amazing. It really is. The question is, what now for the next generation of satellite navigation?
Well, it's about to get even better. The European Space Agency is launching its very own answer to GPS, Galileo, which will see 30 new navigation satellites in orbit over the next 5 years.
I'm quite nervous, actually. We're in quite a privileged position here. We're one of the very few crews who've actually been allowed in here. Behind that door is a very top-secret room where they're building Galileo. We all use the American system at the moment, GPS, and that's 30 years old. And Galileo is the new generation that proves to be more reliable, more accurate to cope with the demands of the future.
Dr. Mike Hughes is leading the development of the system and shows me the inside of one of the new satellites.
Let's start at the beginning. Why Galileo? Why do we need this? Because we've got a GPS system up there already.
There are limitations to the accuracy of GPS.
Yeah.
There are limitations to its availability. The European Union took the decision that we were becoming too dependent on a system we didn't control. I mean, GPS is a monopoly system.
And it's an American system.
And it's an American system. Right. And even being a trusted partner...
It's really useful to have your own just in case. Is there one thing that makes this
thing that
really
really stands out, I think, is the clock technology, the precision of the clock technology. We have actually 4 clocks here. There's 2 mesas. These are the big, shiny silver boxes.
Yeah.
And 2 rubidium clocks.
Right. And these are sort of atomic clocks, like super accurate clocks.
Yeah. So the mesa, for instance, takes 3 million years for that clock to lose 1 second.
That's pretty accurate. The clocks that are up there at the moment, the ones that are on the GPS system, just by way of comparison,
they're about 10 times worse than that, so they're still pretty good, and that's the rubidium clock, so about 10 nanoseconds per day.
Yeah, so better time, better accuracy.
Yeah.
It's funny to think that GPS, once designed as a military application, has changed our lives to the point that we just completely take it for granted. But what I find exciting are the future applications, the things that nobody's yet thought of that Galileo could be making a reality.